Synchronous generators. Definition. The synchronous generator or alternator is an electrical machine which converts the mechanical power from a prime mover into an AC electrical power at a particular voltage and frequency. The synchronous motor always runs at the constant speed called synchronous speed. Usually it is used in three-phase voltage. Single-phase voltage are also available but not widely used. Working principle of synchronous generator. The synchronous generator works on the principle of Faraday laws of electromagnetic induction. The electromagnetic induction states that electromotive force induced in the armature coil if it is rotating in the uniform magnetic field. The EMF will also be generated if the field rotates and the conductor becomes stationary. Thus, the relative motion between the conductor and the field induces the EMF in the conductor. The wave shape of the inducer's voltage always a sinusoidal curve. Characteristic of synchronous generator. Synchronous machines are principally used as alternating current AC generators. They supply the electric power used by all sectors of modern societies: industrial, commercial, agricultural, and domestic. Synchronous generators usually operate together or in parallel, forming a large power system supplying electrical energy to the loads or consumers. Synchronous generators are built in large units, their rating ranging from tens to hundreds of megawatts. Synchronous generator converts mechanical power, AC electric power. The source of mechanical power, the prime mover, may be a diesel engine, a steam turbine, a water turbine, or any similar device. For high-speed machines, the prime movers are usually steam turbines employing fossil or nuclear energy resources. Low-speed machines are often driven by hydro turbines that employ water power for generation. Smaller synchronous machines are sometimes used for private generation and as standby units, with diesel engines or gas turbines as prime movers. This is the diagram of basic principle of synchronous generators. How does the synchronous generator works? Electromagnetic induction. It is said that if a winding rotated in a homogeneous magnetic field, a voltage will be induced into the winding, which means that the rate of flux change determines the strength of voltage. To generate electricity in the coil, either the coil should rotate with respect to magnetic field or a magnetic field should rotate with respect to the coil. In the case of generator, the second one is used. The rotor and stator are the rotating and the stationary part of the synchronous generator. They are the power-generating components of the synchronous generator. The rotor has the field pole, and the stator consists the armature conductor. The relative motion between the rotor and the stator induces the voltage between the conductor. Rotor produces a rotating magnetic field. Armature coils are stationary, and rotating magnetic flux associated with the rotor induces electricity in the armature coils. Kind of rotor shown here is known as salient pole rotor. For gaining better insight of its working, let's consider a rotor with just 4 poles. Rotor coils are excited with a DC power source. The rotor is made to rotate by a prime mover. This makes the rotor flux also rotate along with it at the same speed. Such revolving magnetic flux now intersects the armature coils, which is fitted around the rotor. Magnetic flux will generate an alternating electromagnetic force across the winding. Since 4-pole rotor has got 2 pairs of north and south poles, so when the rotor turns a half revolution, the induced EMF takes 1 complete cycle, so it is clear that frequency of the induced EMF is directly proportional to the number of poles in rotor speed. It can be easily established that frequency of induced EMF, rotor speed, and number of poles are connected through the following relationship. It is clear from this relationship that frequency of electricity produced is synchronized with mechanical rotational speed. For producing 3-phase AC current, 2 more such armature coils which are in 120-degree phase difference with the first is put in stator winding. Generally, one end of these three coils are star-connected and three-phase electricity is drawn from the other ends. Also, it is clear from past equation that in order to produce 60 Hz electricity, a four-pole rotor should run at following speed of 1,800 revolutions per minute. Such huge RPM will induce a tremendous centrifugal force on poles of the rotor and it may fail mechanically over time. So salient pole rotors are generally having 10 to 20 poles, which demands lower RPM. Besides, salient pole rotors are used when the prime mover rotates at relatively lower speed from 120 to 400 RPM. Pole core is used to effectively transfer magnetic flux and they are made with fairly thick steel lamina. Such insulated lamina reduces energy loss due to any current formation. DC current is supplied rotor via a pair of slip rings. This DC current is supplied either from an external source or from a small DC generator which is fitted on the same prime mover. Such generator are called self-excited. With variation of load, generator terminal output voltage will vary. It is desired to keep the terminal voltage in a specified limit. An automatic voltage regulator helps in achieving this. Voltage regulation can be easily achieved by controlling the field current. If terminal voltage is below the desired limit, regulator will increases the field current, thus the field strength. This will result in an increase in terminal voltage. If terminal voltage is high, the reverse is done. Equivalent circuit. The voltage EA is the internal generated voltage produced in one phase of a synchronous generator. This EA is not usually appears at the terminals of the generator. Only time the internal voltage EA is the same as output voltage VF of a phase is when there is no IA flowing in the machine. Why VF is not equal to voltage EA? And what is the relationship between VF and EA? The answer for these questions are based on the equivalent circuit of synchronous generator. Factor that causes the difference between EA and VF. The distortion of the air, which is called armature reaction. The self-inductance of the armature coils. The resistance of the armature coils. The effect of the salient. By exploring first three factors, a machine model can be formed. The effect of the salient pole shape will be ignored. The full equivalent circuit of a three-phase synchronous generator. A DC power source supplying the rotor field circuit, which is modeled by the coil's inductance and resistance in series. R adjective controls the field current connected in series with RF and LF. Stator or armature equivalent circuit consists of three phases which each has an EA with a series XS and a series RA. The voltages and currents of three phases are 120 degrees apart in angle, but otherwise the three phases are identical. Three phases can be either star or delta connected. Figure 12.1 shows the full equivalent circuit of a three-phase synchronous generator. Y connection. The terminal voltage VT is related to the phase voltage VF by VT equals 1.732 volts F. D connection. The terminal voltage VT is related to the phase voltage VF by VT equals VF. Figure 12.12 shows the per-phase equivalent circuit of a synchronous generator. The internal field circuit resistance and the external variable resistance have been combined into a single resistor RF. Types of synchronous generator. The generator consists of two main parts, the rotor and the stator. The rotor is the generator part which is used to produce the magnetic field by connecting it with a DC power source. The stator is the part of the generator which consists of coils. The coil is used to intersect the produced magnetic flux inside the magnetic field. By doing so, induced currents are produced inside the coil. There are two types of method that can be used to intersect the coil with the magnetic flux: armature winding and field winding. Armature type. The first one is known as the armature type or armature winding. In this method, the stator part is placed as the inner part and the rotor part as the outer part. The rotor will produce the magnetic field once it is connected to a DC power source. At this moment, the stator part will be rotated with respect to the magnetic field and starts generating the alternating current. Field type. The second type is known as the field type or field winding. For this type, the rotor which produces the magnetic field is rotated with respect to the coils. The rotor is rotated by a prime mover which makes the rotor flux rotate along with it at the same speed. The armature coils are then fitted around the rotor. This will eventually generate an alternating electromotive force across the winding.